Hello, can you hear me? I hope I'm also able to see the screen.
Yes.
Okay, thank you, Vivek. Yeah. So we have been looking at evolutionary dynamics over the last week, I think, right? Let's continue that. Okay. So we wrote down this equation, delta P, which is the rate of change of frequency of some allele, is proportional to P into 1 minus P times the differential fitness of that allele with that of other alleles, right? Okay, and we sort of tried to look at how to also analyze what we call strategies that animals take, right? We studied that in the context of hawks and doves, and how we get some interesting strategies that animal adopt. Okay, and so what I will do today is try to see, if we can sort of think of a more general formalism than what I have written here. By the way, are you hearing a lot of background noise? Are you hearing when I'm speaking? Do you hear a lot of background noise, or is it okay?
Yes, there is some background noise.
Is it too bad?
No, I guess not.
It's not too bad. Okay, fine. Yeah. So because I'm using an earphone, I hope it's fine. Okay. So and in the this is as I mentioned, this is also called the replicative equation. Okay. And as I meant, and prior to more recent mathematical sort of framework of evolution, there were other equations that people used to understand evolution. There was something called Breeder's equation. Okay. And then there was something called causal analysis. And then there was another important concept called Fisher's fundamental theorem of natural selection. Okay. Okay. And let me just state what this is. This actually was by Fisher. He stated this in 1930s using some cryptic mathematical and semi-mathematical arguments. Basically, what he said was that the rate of evolutionary change is equal to genetic variance of the fitness. And he argued this is an extremely fundamental statement about evolution. Okay, and so since then it's known as Fisher's fundamental theorem of natural selection. Okay, now what I will now do is, I won't go into this in much more detail. What I will do is I will try to now derive very simple but also very general framework that actually combines all of the previously known stuff about evolutionary dynamics in a single equation. Okay, so let's try to do that. Okay, so let's say that let's say you are at generation T. Okay, there are n individuals. Okay, and let us say the ith individual has a trait given by Zi. Okay, Zi can be a continuous trait. It could be a discrete trait. If it's a continuous trait, Zi can take numerical values, continuous numerical values. If it's a discrete trait like eye color or presence of some specific phenotypes, okay, then it can take values of 0 or 1, presence or absence. Okay, so I'm not so the whatever we're going to do next will be applicable to both. It could be +1 or -1 in the discrete cases, or it could be a continuous value like a height of an individual, right? In such a case, this will be a continuous value. Okay, and let us say that this ith individual reproduces okay, and then gives rise to an offspring who has a trait Zi prime. Okay, this Zi prime need not be same as the parent, right? It could be slightly different from the parent. So we denote that by the fact that there is a deviation from parent's trait by delta Zi. So this delta Zi can be positive or negative. Okay. And we also assume that Zi has a fitness omega I. Okay, meaning this individual, ith individual, will have omega I number of offspring. Okay, so this is, let's say this is what has happened now. Okay, so now how do we now go about understanding evolution? As you can see, this is basically slightly general version of what we did in the first class on the evolutionary dynamics. In the first class, we only had discrete traits, right? And then we were measuring the proportion of individuals in this trait versus the other trait after the reproduction, and we had ignored this delta Zi. We did not account for the fact that offspring can be different from the parent. Okay, so now we have done this. Okay, so there are n individuals. So this is the new generation now at t+1. Okay, this is t+1. So how many individuals are there in the t+1 generation now? So there were, for every individual Zi, how many offspring are there now? Wi number of offspring are there, right? So if there were n individuals in the previous generation, what will be the new number of individuals? That will be n times omega bar. Do you agree with this? This is basically the previous number of individuals times the average fitness of the entire population. Okay, where omega bar is basically this. You all agree with this? A new number of individuals will be n times omega bar. Okay, so let me also introduce some basic statistical quantities here. So if we have n individuals having traits Z1, Z2, so we can denote Z bar to mean average, which is basically summation of all individuals' trait divided by the number of individuals. Is that fine? Okay. And likewise, we can also define an average fitness, right? That would just be summation of all individuals' fitness divided by n. Okay. Now, how many of your, so I'm assuming that just like mean, you also know what is variance, right? What is variance? Variance is nothing but Zi minus Z bar square divided by n. Is that fine? So you know what is mean and you know what is variance. How many of you know what is something called covariance? Do you know what is covariance? Let's say consider you know, covariance between two variables. In this case, we have two variables as Z and W. What is covariance? Covariance is basically this. Okay, so it's summation over all individuals. But now there are two, so it's something like variance. So covariance is something like variance, except that we do the following. Is it fine? Do you understand what it means? So imagine a scenario when Z and W are totally independent variables. Okay, the covariance will then be 0. Okay, so if so, you expect that the covariance between Z and W will be close to 0. Okay, it will not be exactly 0, but it will be close to 0. Okay, and consider a case when Z and W are very closely related. Okay, then covariance. So to sort of understand that, assume that Z and W what do you think will be the value of this? Okay, to understand that, there is a formula that actually will be very helpful. There is a theorem that shows that covariance between two variables is equal to variance of one of the variables times the slope of the regression line between the two variables. Okay. So what do I mean by that? Let me just try to explain that. So to understand this better, let's just draw a graph. Okay, let's say this is Z, this is omega. Okay, consider the case when there is no relationship between the two variables. Okay, they are all both independent. Okay, now if you use this formula, what will be this? Now let's do a regression between these two variables. What do you think the regression will look like? Something like this, right? Will the value of m be large or small? The slope of the regression line. So all of you understand, I am hoping, that what is the slope of a regression line? All of you know what is a regression, right? You would have studied regression somewhere in your probability and statistics course. Okay, I think it's reasonable to assume you know what is regression. So if you do regression between these two variables, now you'll find some slope for this line. Let's call that m. What will this m be in the case that I have drawn? It will be close to 0, right? So what that means is the covariance between Z and W therefore will be 0 because the m itself is 0. Okay. Now consider another case where they are very tightly related like this. Okay. Now for this set of green dots, if I now do a regression, it will look like this. Right? The straight line, it won't be a curved line. So slope will be some value which is non-zero, right? Okay. Consider a hypothetical case where there's actually a linear relationship with slope 1. Okay, which means omega and Z are basically same. In that case, what happens to covariance? So covariance in that case basically becomes variance of Z times 1 in that very special case, right? Something like this. If m was indeed equal to 1, then we have something like this. But if m was a larger number, then imagine a cluster of data that are much more steeper, then the covariance will be even larger. Okay, so okay, so this is something that's going to be useful today. So we're going to use this. Okay, we are also going to use this today. Okay, and we are also going to use this definition of the mean of means. Okay, and this. Any questions before I go forward?
Sir, can we not use variance of omega times slope?
You can, of course, you can observe, just flip the axis. Yeah, you can do it.
But then the covariance will vary, right? I mean,
Huh? You
the
think it will?
covariance value might vary, right?
You think it will? Just think about it. No, it won't. Huh?
Okay.
Okay, so
Isn't it technically plus minus one? Where's it?
what is plus
Depend-
minus one? Sorry.
The covariance, depending on whether they vary positively or negatively.
No, that's not right. I think you're confusing between what is called correlation and covariance.
No,
That's
so
when
if that slope was negative instead of positive, the regression line was negative, then the covariance would be negative. Right?
But you
Minus
said
one.
plus minus one, right?
I mean, instead of one, what you've written where z into one as the approximation.
But for that was for the specific case of m equals to 1.
Right, yeah. Sure, okay.
Yeah, it was specifically for this green set of dots.
Right.
Maybe I'll use the green line. Okay. So one possible confusion you might end up is you have also heard of something called correlation. Okay. So correlation between two variables is basically covariance between two variables divided by standard deviation of one of them times the standard deviation of the other. Okay, so this correlation is bounded between -1 to +1. Okay, whereas covariance is bounded between the variance of the variance of the variables themselves. Okay. Okay, so now there is one more relationship that's actually going to be helpful. Let's go back to this sort of full expression here. Okay, and then simplify this expression a bit. Okay, so we have covariance of z comma omega that is equal to what I'm now going to do is I'll just expand the numerator. Okay, so that will give me zi omega I minus z bar omega I minus and then what's the next term? Sorry, zi omega bar plus z bar omega bar. Did I write all the four terms? Okay. So let us go further. Summation. Now let's take the summation inside. Okay. So I have summation of zi omega I. Okay. And then we have summation z bar comes out, right? Z bar summation omega I. Okay. And then here omega bar summation zi. Then we have summation z bar omega bar. Is that fine? So I have basically taken summation inside for each of the term. So first term, we can't really do much. Okay. What is the second term? Second term is summation of omega I. If I scroll up a bit, I will know the summation of omega I is nothing but n times omega bar. Is that fine? So this is n times omega bar. So this entire term will become z bar n omega bar. Okay. What about this term? Likewise, it will be omega bar n times z bar. Right? Likewise, what is this term? This is also because summation runs over n times. This is also n times z bar omega bar. Okay. So basically, as you can see, there are three terms, all of which are basically same but with different signs. So I can just cancel one of these terms, these two terms. So what we now have is 1 over n. One over n summation zi omega I minus, okay. So 1 over n now goes inside, okay. And therefore this nn cancels. So what you're left with is basically z bar times omega bar. So covariance of z comma omega can be simplified to this equation. Any questions on the algebra and concepts so far? Okay, so if there are no questions, I will go forward.
What happened to the n?
Which n, sorry? In the
What-
second term?
Yeah.
So, I just took the n inside. You remember these two got cancelled, right? This n is cancelled. The third and fourth got cancelled. What was remaining was z bar n omega bar.
Yeah.
And when I took the n inside, the n got cancelled.
So then, why is n still there in your
It's only for the first term, sorry.
Okay, right. Okay, got it. So,
N is now basically, okay, by the way, what is this term, right? So you have two random, variables z and omega, right? I'm taking the product of them and then summing all of them and divide by total numbers, right? So what's left-hand side is basically the average of, we also denote average by expectation values by term E. So the first term is basically average of this product. Is that correct? Average of z times omega, product of two random variables. And the next two terms of this, expectation of z, expectation of omega. Okay. So I have just suddenly introduced a new, symbol here, E. E, sometimes we just write the same z bar as this expectation value. Expectation value means, mean value. Sorry. Okay. It's a useful notation sometimes. So basically, covariance between two random variables z and omega is basically difference between two terms. The first term is expectation of product of the two variables minus the product of two expectations. Okay.
so why did summation z bar omega bar become n z bar omega bar?
Okay. So basically, the last term here, right? So
Yeah, the last.
So what you're asking is, what is this? How do we understand this term? Okay, so summation I 1 to n z bar omega bar. So once you have, so z bar is already an average, omega bar is already an average. Once you have taken average of some numbers, they're basically constants, right? So they have no role to play in the summation at all. Is that correct?
Yeah.
So I can write this as z bar omega bar summation I is equal to 1 to n of number 1. So I'm just writing, number 1 here, just so I don't leave it empty. So it basically means I'm just adding one n number of times. So that becomes n z bar omega bar. And even simpler way of thinking it is I'm just adding z bar omega bar n times. What do I get? That is n times z bar omega bar, right? Is that correct? Is that fine? Okay, so this is equal to so this again is is a handy thing we're going to use today. Okay, so basically although I started off with saying Z is the trait value and omega is the fitness of the trait, so rest of everything on the right hand side I have done is applicable to any two sets of variables. They have nothing to do with, as of now, they have nothing to do with trait and the fitness. Okay, so all of these are simple statistical definitions. So just a revision of basic statistical definitions, basically means, variance, and covariance. So means and variance is something most people do learn. You also learn correlations, right? But covariance is basically nothing but correlation times the product of two standard deviations of the two variables. Okay, so covariance is nothing new in a conceptual sense. Okay, it's a quantity we do use in when we are calculating correlations. Okay, what we have done is basically written down a mathematical expression for the same. Okay, so let me go to the, let me complete what I wanted to do now. So what do we want to do? So let's just go back to this. So time t, we have all these individuals, n individuals who have these traits z1, z2, zi, all the way to n. And then they reproduce with fitness omega I to give rise to zi, who could be different from the parent by delta zi. Okay. So what do we want to do in when we're understanding evolutionary dynamics? We want to understand how the mean trait values change with time. Okay. So in other words, we want to know what is if Z prime represents the new generation, we want to know what is the mean trait value in the new generation, which will be Z I prime divided by what will be the denominator here? You remember I made a remark, if there are n individuals in the first generation, if each of them has omega I number of offspring, where I itself is variable, right? What will be the new number of individuals? It will be
n into omega capital N.
N omega bar, right? Or n times the average fitness value, right? So the denominator here must be N omega bar. Is it correct? Okay. So average of, so basically the number of individuals now has changed. Therefore, when I'm calculating the average trait value of the new generation, I must also divide by the new number of individuals. Okay.
So shouldn't it be the summation would go from 1 to n omega bar?
So summation, see, because the way I have written, the summation is still, oh, right. You're right. Okay. So this summation here technically should go all the way from, 1 to n, but I think I made a small mistake here. I'll just keep it still as n. I will still keep it as, a parent and an offspring, but offspring need not be a single individual. It could be multiple individuals. So basically what I should be doing is omega I times zi prime. So each offspring, each of these zi primes, actually there are omega I number of them. Now is this fine? The dimension is still goes from 1 to n, but the numbers still are actually an omega bar. Is it fine?
Yes.
Okay. So now what is Zi prime? Zi prime is basically this. The parent and the difference. Of course, the assumption here is that every one of the offspring has the same delta Zi. Okay. That's not necessarily a required assumption, by the way. Okay, but one can even relax that. It doesn't really change the equation that we're going to get in the end. But for the today's calculations, let's just assume that. Okay, so and then we have n omega bar. Okay. Let us simplify this, which is basically split this into two terms. So I have 1 in omega bar, right? The first term will be omega I zi. Okay. The second term will be 1 in omega bar, right? Summation omega I times delta z. Okay. So what is the second term? What does second term mean? So there is a delta zi, that is a difference, right? For each of the offspring, right? And then you're weighing them by omega I, depending on how many offspring were there for the ith individual. So if I take this omega bar outside, what this basically means is that this. Is that correct? It's the expectation value of the changes in the traits, but you weigh it by how many offspring with that change happened. Is that fine? So only the second term, I'm just writing it in the following. Sorry, I made a mistake here. So the denominator omega bar is there, but not the second term. I'm writing it this way. Okay. So now what we want is not just the average state in the new generation. What we would like to do basically is also what will be the trait in the differences in the traits over generations, right? So what I'm interested really is delta z bar. How much is the trait change over one generation? Okay, that is nothing but z prime bar. That's the new trait average minus the old trait average. Okay. So new trait average, we have just done this calculation. There are two terms. The first term is this, which is omega I zi into n. That's the first term. The second term I have written in a new way now, which is 1 over omega bar e expectation of how the parent offspring differences in traits happened, and you weigh it by fitness of each of those parents. Okay. And then you now have the new term, which is the minus term, minus z bar. Minus z bar is nothing but summation of zi over n, 1 to n. Is that fine? Okay. So I will just, what I will now do is I'll just keep this term the way it is. I'm not going to do much with this term anymore. So let's now work with the first term, the last term here. Okay. This is 1 n omega bar summation omega I zi minus. So I have this term here. Let's do something, which is, let us multiply and divide this by omega bar. Okay. So I'm multiplying and dividing this by omega bar. Why am I doing this? That way I will have the same denominator for both of the terms. So I will now have 1 over n omega bar okay, let me write it in the following way. Yeah, that's fine. Omega bar and summation zi. Is that fine? Okay. So in fact, I can simplify this a bit further by taking this 1 over n here. What will this term now become? That will be basically z bar. Okay. So this term is basically now z bar. So we now have 1 over omega bar summation omega I zi divided by n minus 1 over omega bar omega bar, Z bar. So these are all basically literally just adding terms, right? I'm just, while adding terms, I'm just making it convenient and rearranging terms. Okay. By the way, I haven't forgotten the fact that there's also a third term here. That will continue. Is so far everything fine? Now, what is this term? This term is nothing but expectation of omega Z, right? Product of the two variables, and I'm taking the average of all of them, right? And of course, what is this term? This is nothing but expectation of the fitness, hence the expectation of trait value. Okay. Okay, so now we have and note one thing following: every one of the term has 1 over 1 over omega bar, right? So what I can just do is multiply the entire equation by omega bar. So left hand side becomes the average fitness times the change in the values of traits over one generation, average change in the mean trait value times the average fitness. What is that equal to? Expectation of omega Z minus expectation of omega expectation of Z, okay, plus expectation of omega delta Z. Is that fine? Are you able to follow all the algebra so far? So let us now go back to the previous page where we noted that EZW minus EZW must be the same as covariance between the two. Okay. So what does that mean? This first collection of these two terms is nothing but the covariance. So we have arrived at our I really prefer writing Z comma omega, but you can write it either way. It's symmetric term. Okay. Any questions? Is this fine? Did all of you follow what we did? Let me tell you what we did. For if you don't worry about the algebra, let me just tell you what did we do in terms of the steps we followed. We had at some generation t, an arbitrary t value. We had n individuals, okay, and each of them had some trait zi, okay, which is I dependent, and then that individual I had omega I offspring who had traits zi prime. And we assume that Zi prime is Zi, the parent state, plus some small deviation. Okay. And we wanted to know what there was, let's say there was some average to this average value of this trait Z. So let's think of Z as height of individuals. Okay. We know that height is a heritable trait, right? And so there was, let's say, a population which had an average height of, let's say, 5.5 feet. Okay. And then in that population, there was each individual had a fitness omega. Okay. And then there was some average fitness for the entire population. And then what we have now done is we have calculated what's the new height. So we want to know what is going to be the new height of this population. So what is the new average height? So there was some Z bar average height. There is the new average height Z prime bar. Okay, we want to know what is this difference between the average heights of two generations if we know the fitness of each of these Z values. That's what we have done. And what we have shown basically is that if each individual I had a fitness omega I with a corresponding Zi, Okay, then you can write down an equation for the differences in the average heights with this formula. Okay, what this tells is that the average changes in the heights, okay, times the the average fitness is nothing but covariance between trait and the fitness. Okay, covariance between trait and fitness plus an average value which comes because of parent offspring differences. Okay, this is also called transmission bias. Which, to be very honest, I really don't understand. For example, one way this can occur is via mutations, recombination, and so on. Okay, what do you think this term represents biologically from what you have studied so far? Let's think of, let's again use this graph, right? Omega is on the y-axis, Z is on the y-axis. Let's say Z is the average height of individuals, and omega is the fitness, right? Now, if the blue line is the sort of line that passes through all the data points, what do you infer from that? The height has no influence on the fitness, right? Okay. Okay. Therefore, the covariance term will be basically close to 0 because n is 0, right? On the other hand, if it was a green set of data points, the fitness and the trait are highly correlated. Okay, therefore, what do you expect to happen to this term? Do you expect more change in the average height in that case? Yes, right? Okay, so in fact, it's actually useful to write this and simplify it a bit further. The first term as variance of Z times the slope. Oh no, slope, I think we usually denote by beta Rm, by the way. Typically, it's, beta in the evolutionary literature. Okay. So again, just, once we write down the covariance in this form, this actually becomes now easy to interpret. What was the first thing that you learned in the evolution? You need to have variability in the traits, right? So what is the first term now? Variance in heritable traits. What is the second term? Second term measures the slope of relationship between the fitness and the average trait and the trait value, right? If the slope is high, what do you usually say? If there is a increase in trait, if there is a strong increase in the fitness, what do you say?
Positively correlated.
Okay, that's just statistical term. Biologically, what do you say?
It's directional selection.
There is actually a selection. Yeah, actually a selection for some values of traits. So basically, beta is a measure of selection. Of selection. I think it's also called selection coefficient. I don't entirely remember. I think selection pressure is probably, so this entire term together captures the effect of natural selection, because natural selection requires both variation and this is called I think a selection strength, I think, or coefficient of selection, if I'm right. Okay, I think I think selection strength must be applicable to the entire population, right? So I think this is called the coefficient of selection. And these two terms put together is the overall, strength of selection. Does that make sense? Okay, so this is actually a very, very mathematically simple and an elegant way of expressing how natural selection and transmission biases together change the average values of traits in the population. Okay, and this is also called, does anyone know? There's a name for this period. Does anyone know? Price equation. Yeah. Who said that? Mahesh. Oh, okay, excellent. Yeah. This is called price equation. Okay. And price equation basically was developed by George Price in early 70s. And then he quickly died. Okay. But this is so what people say is that this price equation is sort of the most comprehensive way of understanding how evolution happens. It basically captures the complete evolutionary change. Okay, it doesn't really miss any important process by which the traits change over time. Okay, and it also nicely captures various things we intuitively learn, right? And so sort of one can say that this is like equivalent of, in my opinion, Newton's laws, because this is extraordinarily general and it captures all the processes very accurately. And every one of this is a measurable quantity, right? So variance of Z is something you can measure, and coefficient of selection is something you can measure. Let's say in experiments, you can plot omega versus Z, right? And then you can measure these, okay? And you just basically multiply them to get the, how the selection is causing changes in, it could be allele frequencies. If Z bar is basically proportion of one allele, then you are measuring allele frequencies. Okay. And how does this relate to the first replicator equation that we derived? Is it clear to everyone? Before I go there, is there any question on this?
I'm still not completely sure what omega bar delta Z bar means, like ecologically, like what is the...
So Z bar is basically the average trait value.
Right, no, delta Z bar. So that's the average change in the trait value.
Exactly, yeah. So let's say there are two there is one population. Just think of an example that might make it a bit easy, right? If there was an average height of, let's say, think of beak length. Okay, if Z bar is the average beak length in generation 1, Z prime bar is the average beak length in generation 2 of some bird species. Delta Z bar is the difference in those averages. If the beak length has increased, delta Z bar will be positive. If beak length, if the beak length has reduced, then it will be negative. Is it clear now?
Yeah, and then when you multiply that with omega bar, what does that?
So the multiplication with omega bar is to simplify the equation. What I think one should really do is keep the omega bar on the right hand side. Okay. So if you forget omega bar, which is not really important to understand concepts, it is important for numerical calculations, but not for concepts. I think maybe there might be something subtle I'm missing there. So forget omega bar. So what it's saying is the change in the average trait values is proportional to covariance between trait and the fitness, plus this transmission bias term. And of course, to get the numerical value, you need to multiply the entire right hand side by omega bar.
Right.
Do you think it helps if we just write omega bar on the right hand side?
I guess, yeah, like I was getting confused what the value of multiplication of the two meant.
Yeah, that doesn't, it doesn't really mean much. Actually, maybe it doesn't mean much. So as recommended by you, I'm going to actually do this.
So in the case of the beak length, what exactly is the transmission bias? Like, what is there a biological meaning to it?
Yeah. So as I said, it could be because of mutations that the parents and offspring have different values of peak length, right? That could be that's one way delta Z can be different. You can have delta Z different because of recombination. So the two simple ways, the parents and offspring are different. Okay, now it's possible that that's entirely unbiased. And delta Z is entirely unbiased, which is a case I'm going to consider very soon. Okay, but there could be a bias to that changes also, right? For some reasons. Okay, for example, if you have a small enough population, even mutations of, even if it's unbiased mutation, right? Okay, mutations may increase or decrease, let's say, beak length by equal, measure, but in a small sample size, you may still see a positive or a negative effect randomly. So therefore, in such a case, the second term will be still non-zero. So that's what the second term is capturing. But because of certain genetic features, it's also possible that there is actually a direction coming from the second term. And second term is also, honestly, be very honest, a bit hard to understand. So now that we have learned this, maybe if we do a few more steps, it might become clear what this is. Okay, let's consider discrete traits or genotypes like we did A and B. Okay, let's say that presence of A, we denote it as 1 and that of B as 0. Then what will be Z bar? Z bar will be proportion of individuals of proportion of population with genotype A, right? And you remember we were denoting that as P in our previous, previous analysis, right? Okay, and and what about the variance of Z in such a case? What is variance of Z when these traits occur discretely? This is something I have not proved, but it's actually a very, very easy thing to prove. That's actually nothing but P into 1 minus P. Okay, this also comes if you take any, for example, if you know something called Bernoulli distribution. In Bernoulli distribution, you have only two discrete outcomes possible. If you know something about Bernoulli and binomial distributions, this result will be fairly clear. So I'm not going to derive that, but I will leave it as an exercise for you to figure it out. But it does make sense intuitively, right? When P is equal to 0, meaning there is no A, everybody is B, the variance is minimum. When everybody is A, P is equal to 1, again it's the minimum. This maximum when P is equal to half, meaning when half the population is A and half the population is B. Again, this makes sense, right? Variance of Z is equal to P into 1 minus P makes complete sense. What will be this beta of omega Z? Remember, beta of omega Z is basically the regression line between, okay, as a function of Z. Now, what does Z become now? Z basically becomes P in this case, right? And you have only two passive, sorry. Z actually has only two possible values it can take in the discrete case. One is 0, another is 1 is 1. Let's say it has a value of omega A when it is 0, omega B, sorry, right? Because everybody is B here. It is at a value of omega A when it is 1, meaning everybody is now 1, okay? The individual has a trait A. So now what is the regression between 2 points, by the way? It's basically a straight line, right? And in fact, the slope is proportional to omega A minus omega B. So in this case, have written omega A is less than omega B, therefore this will be a negative slope. Okay, but I could have also entirely flipped it. So therefore, in this case, this is nothing but omega A minus omega B. And also in this discrete case, do you remember what did we assume about parent offspring differences? Was there a delta Zi at all? We assumed that to be 0, meaning offspring are identical, meaning offspring are identical as parent. Okay, and in such a case, what happens? The expectation value of omega I delta Zi basically becomes 0, because every one of these values is 0. Okay, so now if you put all of these terms and go back to the price equation, what do we get? The left hand side now basically becomes delta P. Okay, the right hand side variance term. The variance term here is basically P into 1 minus P. The slope term is omega A minus omega B. And we have this term omega bar in the denominator, right? And the second term is 0 because we assume that the offspring is identical to parent. And this was precisely the expression we had derived as a replicative equation. Is that right? So whenever you have two equations, and if you can derive one equation from the other equation, which is the more fundamental one, the first one is considered the more fundamental one, right? Therefore, in this case, the simple replicator equation can be derived by price equation, and therefore price equation is a more fundamental equation. Okay. Okay, now what else can we do? We'll do one more final thing, and then we will stop today. Okay, so Fisher said something about how fitness changes over time. So far, we have been interested in how proportion of certain traits change over time, or the average trait changes over time, right? What Fisher said was the rate of change of fitness. Okay, if omega is fitness, delta omega is the rate of change of fitness, is equal to genetic variance in fitness. Okay, so let us see, if price equation is more fundamental than this, can we arrive at this from the price equation? So let's again start with price equation, which is delta Z bar is equal to covariance, not covariance, just to the variance in Z beta omega Z plus let's start by assuming something. Assume that delta Z, or the transmission bias term, is 0. Maybe because the mutations are unbiased, maybe because this is a very, very small term, maybe a combination of all the two. Okay, let's assume this. So therefore, second term goes to 0. Let me ask you the following question. So you have a parent, right? Let's just write this on the right hand side here. So you have a parent I who has a trait Zi. Okay, if there are no mutation, and then they will give rise to an offspring who will also have, and this parent has a fitness omega I. Okay, meaning this trait has a fitness omega I. So, and this parent has now given to again Zi, right? Because there are no mutations, there are no transmission biases. Okay. Now, what will be the fitness of this individual?
WI.
It will also be WI. Okay. So just like the trait is inherited, can we say that omega I is inherited? because traits are inherited. Fitness is inherited because trait is inherited. Do you agree with this statement? I mean, somebody's agreed with me. How about others? Because when you said that the offspring has the same omega as
Like,
the parent,
isn't fitness dependent on the fraction of population?
fraction of population as in?
Like the fraction of A versus like fraction of A and B.
Absolutely, it's a very, very good point. Okay, so whatever I just said is not always true, but let us assume that fitness is inherited. Okay, we know it's not always true, but we know it's not always true. It's a very, very good point. Was that Bevan, by the way? Who
Yes.
said that?
Yes, Bevan.
Okay. For example, it may depend on proportion of genotypes, right? Not just what is your genotype, but what's the genotype of other individuals, right? So it's not always true. Okay. So but let's assume this is the case. So if you assume that is the case, can I treat fitness as a trait itself? So see, this price equation can be applied to any trait, okay, that is inherited, right? Okay, so
but this also
it could be
means
height
that
of the
the
individual.
selection pressure is the same across both the generations.
So like, I'm just doing it for 2 generations, from one generation A to B. I'm not T to T plus 1. I'm not worried about what happens next. Okay.
Okay.
Just across 2 generations. See, everything we have done is just that. Across one generation, what's going to happen? Okay. See, fitness is inherited. We can think of fitness itself as a trait. So therefore, what we can do is we can set Zi to be omega I in price equation. Okay. And if we can do that, what do we get in terms of price equation? The average change in the fitness. Okay, there was actually a 1 over omega bar here, right? Okay. What do we have? We have variance of this. And what is the slope of beta omega omega? It will be just 1, right? So let me just write the full equation in this context. So if I assume that, if I consider the fact that fitness itself is an inherited trait, we have this equation. Is that correct?
So isn't there a omega bar on the LHS?
Oh, thank you very much. I'm like, every time I'm forgetting it. Okay. How is this happening? Something strange. Maybe it's coming out of this one, right? So I can't erase this blue thing for some reason. Okay, you have to live with this, huh? This has happened in the past. Oh, suddenly I went away. Okay, great. Okay, is everyone fine with this? Okay, so now let us apply this. So far I haven't applied the first assumption, right? So I have only assumed that fitness is inherited. But anyway, there is no need for this to be this caveat at all, right? Because if I am keeping the second term, I'm also accounting for the fact that there could be changes in the fitness between 2 generations, right? Okay, so assume fitness is inherited. It's actually correct. There's no assumption at all here, by the way. It's like So it's a biologically very realistic assumption. Okay, and then we set zeta is equal to omega in the price equation. I get this. Now apply this assumption, and therefore we will now set this to 0. This is where I'm applying the assumption that parent and offspring have identical fitness, not just nearly similar fitness. In such a case, what do we get? We get that the rate of change of fitness, the average rate of change of fitness is 1 over omega bar times let us now compare this with what Fisher said. He said that the rate of change of fitness is genetic variance in fitness, and that is indeed the case, right? So variance of omega is the genetic variance in fitness. Why do we call it genetic variance? Primarily because it's an inherited quantity, and of course there's a normalization factor of 1 over the average.
Why did the slope become 1?
Because if you regress the same variable with itself, what do you get? It's 1, right? Yeah. So he basically said that for populations in natural selection, the rate of change of fitness is equal to variance of the fitness itself divided by the average fitness. And what is neat about this is the following. When Fisher made that statement, it was not clear what were the additional assumptions you have to make to arrive at his theorem. Now we do know because of price equation. What's the assumption we have to make? The main assumption we have to make is this: there is no transmission bias. So we know that this is true only if there is no transmission bias in fitness. By the way, just think about what does this, it is not, let's interpret this equation. Left hand side is rate of change of fitness, right? What is the right hand side? Variance of fitness. Can variance be ever negative? Always negative?
Positive.
Always positive, right? So what does this mean? The rate of change of fitness is always positive. What does that mean? The organismal fitness keeps on increasing. This nicely fits in with the idea of the survival of the fittest, right? Okay, except that we know this is true only under this assumption. It's an extremely important assumption. Okay, so I have an assignment question that will help you discuss this a bit more and figure out when it actually is violated. Okay, so with that I will stop here today. Any questions I can take, and somebody wanted me to go over the assignment number question, homework 3. I can also do that if people are interested.
So I have a few questions.
Sure.
Here, while we are saying that this fitness is inherited, so we are considering that the two generations have same omega I, right?
I am not assuming that. Two generations need not have same omega I. I'm just looking between generation T and T plus 1. Okay, and then I'm looking at the difference between the fitness in the first or the second generation.
Okay, so if we are saying that the fitness is inherited, so what actually you just wrote about that they have same omega I, the two generations.
Okay,
here,
so
while you were explaining this, where you have written the question.
So I'm basically treating fitness itself as a trait. Okay, which is a reasonable assumption, primarily because we know that fitness and traits are correlated, right? Okay, and if that is indeed the case, because offspring will also have similar trait as the parent, it is pretty reasonable that the offspring also has same fitness as the parent. So therefore, fitness is inherited.
So like I'm confused in that. So why the delta omega term is not getting 0? Because if they have the same
But the average fitness in the population can change.
so
Imagine
there
there are
is
two,
no change.
no, let's imagine there are two competing genes, two have different fitnesses, right? The proportion of those genes will change over time, right?
Okay.
Let's say there are two genes, one gene has a fitness 4, other gene has a fitness 3. Okay. Okay, let's say they are equal in number in generation 1. What will happen in the next generation? The higher fitness will increase in their frequency, in the next generation.
Yes.
So therefore, don't you think the population fitness will increase?
Okay.
That's what this is trying to calculate.
Okay. So within the, if we are considering the parent and the offspring, they have the same fitness, but on the overall population level, there is a change in the overall fitness that we are accounting.
Absolutely, because the proportion of the traits themselves are changing, the average fitness will also change.
Okay. Okay. Yes.
And that is true. Okay, yeah, go ahead. Yeah.
Oh no. Okay. I had a doubt about what kind of fitness this is. Is this the fitness which the particular trait that we are talking about adds to the total fitness of the organism, or
That's
it
true.
is the total
That's
fitness?
True. It's we are only discussing all else being equal. There are two traits that are there, no? Or Z is the whatever the trait that we are interested in. It's the fitness associated with this trait.
Okay, so all the average
all else being
values
equal, yeah.
are of fitness conferred by that trait.
Exactly. Yes.
Okay.
Yeah. I mean, in other words, if we kept everything else constant, if we varied only this trait, if a trait is varying because of natural selection, right? And if that's the only trait that is now changing, and then how will the fitness change?
Right. So it's different from what we learned in last class about baseline fitness being added to.
So I assume that the baseline fitness is constant. Okay.
Right.
And what is the fitness associated with this trait? Yeah, that's a good point.
Okay.
So I had a question about how Z and omega are related. So in the price equation, we assume that they are linearly related.
No, we don't have to assume that. No. There's no need to assume that they are linear.
Okay, so
because the derivation had no such assumptions, right?
Right.
We go back to the derivation here, right? Derivation, nowhere did we assume that they were linearly related.
I mean, beta is the coefficient of is the slope of the regression line, right? So what if you had like a quadratic relationship between?
It just means that only the linear coefficient, linear regression matters, not the quadratic regression. That's what basically, if you're interested in understanding how the mean trait varies, how the mean trait changes with time, then only the linear regression matters, no other regression will matter. That's the implication of price equation, which is also very interesting, right? It doesn't matter what the relationship between Z and omega is. All that matters is the linear regression. For the mean variable, mean trait. Okay, that's the key. It is possible that if you look at the variance in trait, the answer will be different. Okay. For example, disruptive selection, right? What happens in disruptive selection? You can have the mean trait the same in principle, right? Okay. But the variance in trait is increasing because there are these two modes that are moving away, right? So price equation in this form doesn't capture how that variance is increasing, but it is actually possible to also write a price equation that calculates how the variance is changing. Because price equation, it doesn't care what Z is. It has to be some trait, right? I can also redefine that in any way I like. For just the way we defined it for fitness here, we thought of fitness as a trait now. We can also look at how the left-hand side can be modified to look at how the variance is changing across generations.
Okay. So in that case, so in the case that we have derived, the price equation can only sort of detect, say, stabilizing or directional selection.
The way we have written, yes, absolutely. Yeah. It's most helpful for those. Yeah, the way we have written this, yes. Okay, any other questions? So how many are interested in going over the assignment? Do you have any other questions about the assignment 3? If I'm right, if somebody wanted to discuss assignment 3.
Sir, only the second question.
What was the second question? I have forgotten.
The positive feedback loops in the type 2 functional response.
What is the positive? It's actually not a very straightforward point. Let me see if I can try to explain, because it's not evident. No, we just wrote down this phenomenologically, right?
Yes, sir.
So, so you know, as long as, so you just have to think, what is positive feedback? Positive feedback is something that is some sort of a reinforcing mechanism. Okay. You know, what is it reinforcing in our context? It's the growth. Either the growth gets reinforced or death gets negatively reinforced. So growth goes up. Okay, that's one way it can happen, or the death can go down. So now let's think of some simple examples. Okay, let's say you're in a landscape. You have planted a tree. Okay, now a positive feedback mechanism would mean that let's say I now have a seed that has dispersed. There's a seed here. There's a seed here. Okay. Now, what is the what is the local density of trees around this? What is it? 0, right?
0.
Now, consequently, what do you think will happen to processes that will help this germinate? So for this to germinate, you want less competition. That is happening nicely now, right? But here is the problem. But where are the resources? Now, if water and nutrients are resources, because it's in the middle of a barren area, what might happen? It would mean that the resources that fall in here are also very small.
Yes, sir.
Because the moment they say the water falls there because of rainfall, it also gets rapidly evaporated. It will run off. Okay. In contrast that with this here, there is of course competition, which wasn't there in the previous one, right? What happens here in this case? Because there is a shading, there will be more water retention. There will be higher chance of the seedling growing to an adult tree, right? There's a higher chance of germination, higher chance of seedling, going to a tree. Okay. So what that basically means is that presence of, the tree reinforce the growth. Okay. So this is a positive density dependence that's happening in this case, right? Here it's a negative density dependence, right? Because what's happening here is that because there is hardly anything, the growth rate is negative in these areas. Okay. So if you want to now write down f as a function of rho without worrying about all of this, let's say you need a threshold number of trees. Okay. Let's call that rho c before the germination and successful growth to adult happens. Then what that means is that, we have a negative growth rate between 0 and rho. It then goes to a positive growth rate. It then eventually, competition will eventually take over. And this is how your growth rate curve will look like. So this is the area of, negative feedback. This is the area of positive. So people also say both of them are sort of, positive in the following sense that, absence of something is causing, absence of that again, right? So in some sense, both of them can be, they're on this side, it's positively reinforcing the lack of trees. On this side, it's positively, once you're above this threshold, you're positively reinforcing presence of trees. Okay, this is the broad idea of, how positive feedback can be defined. Now the question is, how do you now explain this in the context of, the harvesting model, right? So what I recommend you to do is, maybe write down split f into, you want to associate something to the second term, right? So you just have to do the following. I would recommend the following. I would write maybe logistic term as a function of rho. Also write the harvesting term as a function of rho. Logistic term just looks like this, right? Harvesting term looks like this. And now combine them, right? So how is something like this happening for the harvesting model? Okay, so you can think about that and then try to formulate your answer in the appropriate way. So I think what happens is that, so it's a bit strange the way it happens. By the way, what I have written is, sorry, so I have written per capita for L. See, this is a mistake. This is the per capita, right? I should also do the same thing here. Per capita looks like this, no?
Yes, sir.
See, there is a high growth rate, but also a high harvesting rate per individual. Okay. Okay, here what happens is that although the per capita growth has reduced now for larger densities, the per capita risk has gone down. Okay, and that sort of acts as a positive, that because it's happening in a sort of in a non-linear way, it's very crucial this happens in a non-linear way, right? Imagine if it was this, you will not have positive feedback. It's only because of something like this you will actually find that kind of, you will eventually get to something like this. Okay, so I would like you to think and try to see how exactly you will you can. So this is actually not a trivial question. This is precisely why I gave it to you. How to argue the positive feedback growth for this model. I think combine these two and write the full function and then see how different terms are contributing. Okay, and I think you will be able to find the answer. Okay.
Okay, sir. Okay, thank you.
So I think what's happening is for small densities, harvesting is more than the logistic growth itself. But once there are sufficient number of individuals, the per capita risk has now gone down. Okay, and the logistic growth is now above that, above a threshold value, and I think that sort of acts as that if you can interpret as some kind of positive feedback, that will be fine. Okay.
Okay, sir. Yes, sir.
So positive feedback you have to interpret from the logic, largely from the harvesting term. Okay, anything else? Okay, so if there is no other question, I will stop the class now. Thank you.
Thank you, sir.
Thank you.